Welcome to The Explainer. Today we're setting off on an incredible journey together. We're going to uncover a historical detective story that'll absolutely change how you view modern science. You know, we hear about climate change all the time, right? But the mathematical roots of this whole topic are surprisingly old, deeply fascinating, and completely intertwined with a quest to solve one of the Earth's greatest geological mysteries. So how do we know we can trust modern climate models? It's a question we hear constantly, and honestly, it's a completely fair question to ask. The Earth's climate system is overwhelmingly complex, and today's supercomputers process literally billions of data points to project our future. But to find the deeply proven answer to this question, we aren't going to look at modern supercomputers. Instead, we're naturally going to step back in time, all the way to the 1800s. Part 1. The greenhouse paradigm, the core physics. Okay, let's dive into this. This visually captures what we call the greenhouse effect. Notice the yellow arrows coming in from the sun? That solar radiation passes right through our atmosphere largely unhindered, heating up the Earth's surface. But in turn, that energy is re-emitted as infrared radiation, those orange arrows you see pointing back up. Instead of just escaping into the void of space, a huge chunk of this infrared heat is absorbed in the atmosphere by gases like carbon dioxide and water vapor, and then bounced back in all directions. Without this natural blanket, Earth's average temperature would plunge to a freezing -21 degrees Celsius. No way we'd survive that. Now, what you really need to take away from this is that the greenhouse effect isn't some modern guess or a recent scientific fad. Not at all. It's governed by a principle called radiative transfer. This is the fundamental, undeniable physics describing exactly how radiation passes through and is absorbed by the atmosphere. It is the very heart of the climate system. And this brilliantly illustrates just how deep the roots of this science go. Back in the 1820s, Joseph Fourier first realized the atmosphere retains heat. By the 1860s, John Tyndall ran lab experiments proving that carbon dioxide and water vapor were the exact gases absorbing that heat. Fast forward to 1896, Svante Arrhenius built the first numerical model. And in 1938, Guy Stewart Callendar proved the link between fossil fuels and warming. This shows us exactly how progressive and established this century-old science really is. Part 2. Arrhenius and the Ice Ages, the pen and paper era. Meet Svante Arrhenius, a Swedish physicist, sitting right there in his Stockholm laboratory. Now, in the 1890s, the scientific community was fiercely debating what caused the ancient ice ages. I mean, how could the Earth get so cold and then warm up again? Arrhenius built the very first climate model purely out of curiosity, to see if shifts in carbon dioxide could explain those massive prehistoric freezes. He wasn't warning about the future. He was trying to solve a geological mystery. And keep in mind, this was 1895. He had no computers. He didn't even have a basic calculator. He painstakingly crunched an estimated 10,000 to 100,000 equations entirely by hand. Using lunar spectrum measurements from an American physicist named Samuel Langley, Arrhenius spent a full year doing the most tedious calculations imaginable. Talk about dedication, right? Let's break down his brilliant methodology step by step, because it's the exact same logic we use today. First, he calculated the raw temperature change if you altered CO2 levels. Second, and this is absolutely crucial, he accounted for humidity. He knew a warmer atmosphere holds more water vapor, which is itself a greenhouse gas, amplifying the heat. Third, he mapped these variations across different latitudes and seasons. By logically layering these variables, he predicted that having CO2 would drop temperatures by 4 to 5 degrees Celsius, basically triggering an ice age. Part 3. The carbon cycle connection, tracing the source. So if CO2 changes the climate, where do those massive changes in carbon actually come from? Well, for that, Arrhenius turned to his colleague at the Stockholm Physics Society, geologist Arvid Häggblom. Häggblom mapped the geochemical carbon cycle, providing the missing puzzle piece. He identified volcanoes, weathering, and ocean absorption as natural regulators. But he also noted something else that's super important. Human industry was already burning 500 million tons of coal annually, releasing massive amounts of CO2 right into this natural cycle. And here is the great historical irony of our story. Using Häggblom's data, Arrhenius calculated that if you doubled the amount of CO2 in the atmosphere, global temperatures would rise by about 5 degrees Celsius. The math was remarkably sound. However, he drastically underestimated humanity. He assumed it would take us 1,000 to 3,000 years to burn enough coal to double the atmospheric carbon. He just couldn't have foreseen the explosive industrialization of the 20th century. In fact, Consider this quote from Arrhenius to really grasp the mindset of the era. He wrote that adding CO2 would, quote, allow our descendants to live under a warmer sky and in a less harsh environment than we were granted. Yes, coming from freezing Scandinavia, Arrhenius actually thought global warming would be a fantastic benefit for agriculture and humanity. He literally saw it as a way to hold off the next ice age. Part 4. Collinger proves the warming. Theory becomes reality. Enter Guy Stewart Collinger. He wasn't a world-renowned physics professor. He was a British steam engineer and an amateur meteorologist, but he had an incredibly sharp mind, and he wanted to test if Arrhenius's 1890s math was actually unfolding in the real world due to rapid industrialization. He basically demanded physical proof. Methodically working through massive volumes of data from the Smithsonian, Collinger made 3 massive discoveries in 1938. He compiled global temperature records and found a definitive warming trend. He calculated a 6% rise in atmospheric CO2 since 1880, and finally, he connected the dots, tying 150 billion tons of human-made industrial emissions directly to that atmospheric rise. He proved that the greenhouse effect was no longer just a neat theory. It was an active, measurable trend tied directly to fossil fuels. Part 5. Trusting modern climate models, bridging past and present. Now, what's really interesting about this slide is Collinger's historical finding. He calculated a modest but undeniable 0.3 degrees Celsius increase in land temperatures between 1880 and the late 1930s. Just a slow, steady creep upward. But compare that to this stark, modern projection from Earth system models for the 21st century. We're looking at a projected increase between 1.0 and 3.7 degrees Celsius by the end of this century, depending on our emissions. This visually drives home the immense acceleration of the warming trend that started way back in the coal-burning days of Arrhenius. So how do we trust those massive modern projections? It really comes down to this. Both the 1890s pen and paper math and the 2020s Earth system models rely entirely on the exact same core physics. While modern models add complex, interacting variables like melting sea ice, shifting ocean currents, and cloud formations, the fundamental engine driving the heat, radiative transfer, is the exact same math that Svante Arrhenius used over a century ago. To summarize our central thesis clearly and enthusiastically, we can absolutely trust modern Earth system models because they are just the highly advanced descendants of a 100-year-old mathematical foundation. The core physics has never changed. It's practically an unbreakable law of nature. Today, we simply feed that established math with incredibly precise, real-time data from highly sophisticated satellite sensors. And our supercomputers? They calculate in fractions of a second the exact same equations that took Svante Arrhenius an entire grueling year to solve by hand. Which leads us to this final provocative thought. We started by asking if we could trust the models. But knowing what we know now, that the foundation of climate science isn't some new experimental theory, but a deeply proven set of physical laws discovered in the 1800s, the real question isn't about the math at all. If the math hasn't changed in over a century, why are we still waiting to act? Thank you for joining me on this explainer. I hope this journey has totally transformed how you see the history of our planet's climate.